Hey, right. Yeah, because certain carbonyls in school yet. Thursday, or like you haven't started yet, right? Oh, your school isn't even gone through. Okay, can or gone through already, then tutorial doing tomorrow. No, we don't know yet. They didn't prepare. What the shit? Oh, your lecture only once. Yeah. All this weird. Okay, let me just tell you guys what we're gonna do first. Okay, later when the rest come, I also need to mention all this. Okay, but anyways, okay, let me just tell you a little bit about this first. Okay, today we're doing carbonyl compounds. Okay, but before that, I just want to reiterate two things. Okay, number one, the cheat sheet thing, I already sent the instruction to the group. Okay, you guys are meant to do it as soon as possible, okay, as long as it's before your exam that date. I think it's 24th March. If I'm not wrong, okay, later I'll explain to you what this cheat sheet thing is. Okay, but if you don't get you guys the instructions ready, you can just try your best to do up at least one or two chapters first, okay, before I vet through your cheat. Because I don't want you guys to do like everything already, right? Then just submit one shot to me because you're gonna have to edit a lot. So it's a lot of work for you. Okay, so anyways, that one I will track the progress. Okay, but anyways, I feel that this works a lot for your organic revision. Okay, I mean I tested it with other classes.
So we do one or two chapters first.
Yes, one or two chapters first. Okay, then you send me that, give a bit of feedback. Then at least, right, okay, the following chapters, you know what is required, what I require of you guys. Okay, but I give you a bit of instructions in the WhatsApp chat. Okay. Generally speaking, right, I don't want to restrict the format in which you guys prepare the GP because at the end of the day, it is up to your own preference, right? Okay, I want to just have certain criteria inside. Okay, however you want to do it, right? It doesn't really matter. Okay, as long as all the criteria that is in the message is fulfilled inside. Okay, but anyways, the second thing is during the March holidays, right? I need you guys to come down once free, not a charge lesson to do a mock test because no choice now. Okay, we need to get used to the time practice and all that. Okay, so so it's a preparation for your exam because I feel that your March exam right has quite a few topics as well. Okay, so that is your March holiday mock test. I'll reiterate that later again once some of the rest come. Okay, but today I want to touch on carbonyl compounds. Okay, so generally speaking, right, I feel that this chapter is quite simple. Okay, as in terms of content, there's not much. Okay, but of course, in terms of the mechanics, right, I think it's a little bit challenging. Okay, today I can basically cover a few things. Okay, I can cover all the reactions, I can cover all the synthesis, okay, regarding your carbonyl compounds. And the main idea for today, right, is this thing called nucleophilic addition. This is the main idea, okay. I do not want to really spend much more time on this. Okay, so anyways, we have nucleophilic addition. That's the main thing for today. If you all know each other. Okay, so when it comes to nucleophilic addition, right, there are a few things that we have to take note of, but I'll come to that once we finish up everything else that's necessary. So, okay, so guys, take a look at the first page. Okay, first couple of pages, I don't really have to explain much. Okay, it's just your naming convention. Okay, there's just only one thing that I need to focus on, right, for aldehydes and ketones. Okay, anyways, I'm sure in the previous chapter, you have already seen how an aldehyde and ketone looks like. Okay, recognize the functional group. Okay, an aldehyde has one alkyl group, a ketone has two alkyl groups. Fundamentally, both of them have the CO double bond. But of course, ketone has two alkyl groups, aldehyde only has one. Okay, then the other thing on the aldehyde is just a H. Okay, just pay attention to how it looks like, because there are few properties you only need to know. Aldehydes and ketones, they fall under carbonyls because I need you all to take note. They are functional group isomers. Now, of course, in the exam, right, you guys will just probably tell me structural isomers, right? But to be more specific, it's functional group isomers, where you have the same molecular formula, but different functional group. Okay, you guys probably write this down also. Same molecular formula, different structural formula, right? But in this case, to be more specific, there's a different functional group. Some of you guys, right, think that functional group isomers means Same functional group, but then the functional group is in different positions. No, that's not how it works. Okay, it's slightly different over here. Okay, but anyways, okay, to prove that they're the same molecular formula, I need you to also take note, they have the same general formula. CnH2nO. In other words, if they give you this molecular formula, right, it is not possible to tell whether it's an aldehyde or ketone straight away. So in elucidation questions, right, you need to pay slightly more attention because you can't just assume it's an aldehyde nor a ketone. Okay, then? But a few more specifics that I want to get into, then after that, the names and all that, I just want to move on. Okay, so guys, can you perhaps, right, just tell me what is the name of this compound? Okay, you must join examples, right? If you don't join examples, right, you cannot name the compounds yourself. Okay, so first of all, what is the most important thing you need to identify? Okay, number of carbons, yes. Okay, but something even more important is the functional group, right? Okay, so it is an aldehyde ketone first. Okay, it's a ketone, right? Okay, a ketone with 5 carbons, so it's called what? 5 is what?
Oh, 10.
Okay, 10, right? Penta, because pentagon, right? 5 carbons. So pentanone. Make sense? Okay, no worries. Okay, so pentanone with 5 carbons. Now that's very simple, right? But is there something else we need to specify also? Okay, where the double bond is, right? Okay, you always need to specify where the functional group is. So in this case, it's penta what? Penta 1. Okay, this is first carbon, also this second carbon. So penta 2-one. Okay, now simple. Now, can someone tell me how about this? Very quickly, it's not very simple. Okay, same thing, right? It's just pentan 3-one. Now, the reason why I'm going through these 2 examples because I need you to tell me what's the relationship between these 2 guys. What kind of isomers? Are they functional group isomers? Wait, do they have different functional groups? No, right? Aldehyde and ketone then are functional group isomers. So what's this? Okay, now if you tell me structure, right, you're always correct. So this is structure isomer, this is structure isomer, also correct. Okay, but let's be a bit more specific because I realize some of you guys, right, your isomerism a little bit weak. No, chain is your straight chain and branch. There's only one more, not stero. Hey guys, stero is completely different from structure. Over here, right, we call it positional isomers. Okay, positional literally just means the position of the functional group is different. Right, okay, on the second position and on the third position. Okay, I'll ask you guys some more questions. We're not really done here yet. Okay. Okay, chain isomer is 1, 2, 3, 4, 5 straight chain, right? Or you get 1, 2, 3, 4, then the 5 you put it over here. So straight and branch chain, that's called chain isomerism. Okay, that one very easy to spot, honestly, so I don't have to do that. Okay, but anyways, guys, okay, I want you guys to name this compound for me. This one. Okay, come try. Okay, I usually don't go through naming on guys. Okay, if you notice, I skip all this naming shit. Okay, because this is usually quite simple, but for LDIs and ketones quite important. What's this? Rob, sure. How many carbons are there? No, 4 1, 2, 3, 4. Okay, 4 carbons. Okay, don't miss out on this. So 4 carbons is butyl. Okay, so what? What was the functional group here? Okay, LDI, right? So it's butyl. Good guess, it's Al. Okay, ketone is own, aldehyde is type Al. Okay, so butanol. So if you okay, make sense? Okay, do I need to specify the position of the functional group? Okay, you all notice here I specify the position, right? Here do I need to specify? How come no need? Okay, but so what? It could be on the first carbon one. Then I just say penta 1L. Why do I not need to name the position of the functional group in an aldehyde? Why? Okay, guys, you look at the functional group of an aldehyde. Can you look at it carefully? Where must the aldehyde functional group be positioned? In a carbon chain. Can it be anywhere? Okay, ketone can be literally anywhere, right? But aldehydes must be on the end of the carbon chain. Go and take note of this. Okay, aldehyde is at the end of a carbon chain. Now, I really don't like going through all this because it's really quite a waste of time. Okay, but I feel that a lot of the times, right, I see so many people confused between aldehyde and ketone. Take note, guys, aldehyde must be at the end. So because it can only be at the end, there's no need to name the position, right? Can I ask you another question? Can aldehydes undergo positional isomerism? I say again, can they undergo positional isomerism? Yes or no? Why not?
You can go to the other side.
Okay, the other side is the same thing, just keep it around, right? But you notice I already say, right, it has to be an hand. So you cannot have different positions of the functional group. If you put it in the center, then what does it become? A ketone, exactly. Okay, so ketones can exhibit positional isomerism. Go and take note, aldehydes cannot. Okay, all this, right, is to help you guys identify aldehydes and ketones in an instant. Any questions so far? Okay, if no issues, we're just gonna move on already, because the next couple of pages are all like nomenclature. Alright. Okay, later I'll introduce more complicated examples. Okay, so I need you all to turn over to page, I think it's 5. Yeah, okay, go over to page 5. Okay, you know me, I've already told you guys many times, I don't really like going through the physical properties. Because once again, all these questions are just to help you check your hand bonding knowledge. But for aldehydes and ketones, I want to go over a particular segment because it's a bit trickier. Okay, so let's go through structure and bonding a little bit, then we will move on from here. Okay, so guys, can I ask you alright? Okay, go and look at the first question on page 5. We need to deal with the structure and the bonding first. Okay, and for an example over here, right, I need you all to draw this particular guy. Okay, basically what I just do, right? Okay, can someone tell me what's the structure of this compound? I don't know. Oh, yes, the functional group, the structure. Okay, structure and bonding. Come. What is it? A clue. Okay, we have different classes of compounds, right? We have giant ionic, we have giant metallic, we have simple molecular and all that. Okay, this one falls under here. Okay, this one must definitely fall under simple molecular structure. Okay, please take note. A lot of the times in exam, they ask you to refer to structure and bonding. If you don't specify the structure and bonding, you will not get your marks either way. Okay, so tell me simple molecular first. And guys, for simple molecules, your bonding you must discuss what? Is it covalent bonding? Okay, you must discuss the intermolecular forces. Yes. Okay. What are the intermolecular forces in this compound? Can someone tell me? Okay, this is an aldehyde or ketone. Okay, it's the aldehyde, right? Okay. You look at the functional group first, right? Okay, is this an overall polar molecule or non-polar molecule? Okay, it's overall polar, right? So you look at this functional group. This is the part that is polar. So because it's polar, it exhibits what kind of interactions? Okay, PD-PD interactions. But can I ask you, alright? Can this guy also exhibit hydrogen bonding? Okay, answer is no. There is no hydrogen bonding. Why cannot? Okay, there's no. Okay, there's O. Okay, good. The H must be attached to the O. In this molecule, the O isn't attached to the H, so there's no way we can form hydrogen bonds. Does that make sense?
Wait, how do we know?
Okay, because CO is a polar bond. Because the overall molecule is polar. Okay? But guys, is that the only interaction in this molecule? What else is there? Okay, from where? Okay, you notice, yes, you can never ignore the alkyl group. The alkyl group is non-polar. So this is what I'm going to describe it as. This is a non-polar alkyl chain, which is held by ID interactions. So you have to understand, right? A gigantic organic molecule usually has multiple interactions, multiple IMF. Once again, guys, okay, structure and bonding for simple molecular, you cannot tell me covalent bonding. Okay, you must tell me the intermolecular forces. So in this case, PD and ID. Okay, I'm not going to go over every box. Okay, so the next couple of boxes I'm going to skip because I think they are very simple. Simple chem bonding, J1 knowledge. Okay. So far, any questions? Okay,
Wait, this one is similar to
yes. Okay, the functional group is different. Okay, but then of course everything we've done.
like polar and non-polar.
Yes, correct. Okay, in alcohol functional group, you all notice okay, over here the OH is what kind of interactions? Okay, this one then is hydrogen bonds because the O is bonded to the H. But then the rest is an alkyl group. Okay, so later we look at an example. Okay, I'll turn over to 2 more pages. Go and find the thing on solubility. I think it's page 7. We're gonna answer that one part. Okay, we haven't talked about solubility in a while. Okay, just to check that we're on the same page, right? I just need you guys to read through this pattern. Okay, they're saying, right, aldehydes and ketones, smaller versions of them, okay, generally are soluble in water. First thing you always need to highlight is that it's soluble. Okay, they will always tell you whether it's soluble or insoluble. Rarely will they ask you to predict the soluble, unless it's very, very obvious. Okay, so guys, when they say soluble, what does this mean? Okay, come, we're gonna draw a diagram. Okay, so let me just draw a very small aldehyde. No, there's nothing to do with it, because remember, solubility, how does it work? Okay, now before you mix them together, they have their own interactions by themselves, right? Okay, and then you have water also separately interacting with itself. Agree first? Currently, they have not mixed each other. But then now, if you put them together, they will attempt to form some interactions with one another. Does that make sense? Our job over here is to identify all the interactions that exist in this scenario. So we start off with the black color interactions are the existing ones. Can someone tell me what is this water over here? What's the interactions between water? Any clue? Water, come. Okay, no, water is not PD, it's hydrogen bonds. Okay, so you have O bonded to H on both water molecules. Okay, but then now your job is to tell me, okay, between the aldehydes, what do we have? Okay, between the aldehydes, what's the interactions? Okay, we have identified 2 interactions here, right? But can you tell me which one is more significant in a smaller aldehyde? Look at the question now, it says there's smaller number of carbon atoms. So PD. Can you see why? Because if there is a smaller number of carbons, which one is less significant now? ID. Can you see that? So our main significant approach is to look at the functional group itself. That's why I purposely draw a very small structure. So a lot of the times you only read the question, you may not explicitly need to explain, but you definitely need to infer. So the PD is because of the polar, this portion over here. And can you tell me, when they try to mix with each other, what's the red color interaction for? Okay, here we can form hydrogen bonds. Can you tell me why you can form hydrogen bonds? Yeah, I feel that some of your hydrogen bonding concept quite weak. Okay, so let's recall everything again. I'm gonna draw an aldehyde molecule and a water molecule. Okay, can someone tell me what are the 2 criteria for hydrogen bonds? If you forget, right, this is the last time I'm going to go through this with you guys. Okay, good. The first criteria is H must bond to F, O, or N, right? What's the second criteria? Okay, good. You also must have, the other guy must have F, O, N with a lone pair of electrons. Now, you have to take note, these 2 aren't necessarily criteria. Each molecule just needs to fulfill one each, right? And then you can form a hydrogen bond. I repeat myself. The molecules don't have to fulfill both criteria. As long as one each, okay already. So can I ask you, all right, the aldehyde in this case fulfills which criteria? The aldehyde fulfills criteria 2, right? If aldehyde fulfills criteria 2, that means water must fulfill criteria what? 1. Does he fulfill criteria 1? Yes, he does. That's why hydrogen bonds can occur. Okay, and for the sake of things, right, I want you guys to draw a hydrogen bonding diagram between aldehyde and water. I'm going to draw this up. Okay, go and draw this first, then later we answer the question. FO. Oh, my bad. Okay, so FON with lone pair that's on your aldehyde, right? Then water just has a HO bond. Go and draw the hydrogen bonding diagram, because if one hydrogen bonding diagram come out in the exam, right, don't expect any of you to get it wrong. It's very easy. Hit this J1 stuff. Okay, later I'll tell you what are the criteria required, okay, to get your full credit. Okay, if not, let's quickly move on from this one. It's not the organic yet. Okay, it's like almost there. Okay, how do you draw a hydrogen bonding diagram? Come, let's take a look. Right, so this guy has the second criteria, right? So I need to see the lone pair being drawn on oxygen. And the oxygen is going to get interacted with what? It's going to get attracted to what? The H of water. So just instantly draw the interactions with H. But how do they attract each other in the first place? It's because they have what? The partial charges, right? Good. Hydrogen has partial positive, oxygen partial negative. But this is not enough, guys. Your partial charges must be in pairs. Okay, partial charges must come in pairs. So let me show you guys the criteria to get your full credit. It's only 3, it's not hard to remember. Number 1, I need to see partial charges, but once again, reiterate that it's in pairs. If they're not in pairs, they might mark you wrong. Number 2, you must make sure your lone pair of electrons is very clearly shown. So in this case, guys, you see my oxygen here, I bold the lone pair. Because sometimes if you draw very small, your examiner might overlook it. Okay, you don't want them to have a lapse in judgment, right? Then your marks just lose like that. Okay, no, I'll just remove any semblance of dot. Okay, so the third one is, of course, you just need to label your hydrogen bonds. Basically, what I've done over here, it's not that difficult to fulfill this criteria. Okay? Hey guys, okay, can you tell me, you come back to this interaction here. Hydrogen bonds, is this a strong interaction, generally speaking? It's quite strong, right? So if it's strong, that means what will happen? What will happen to the existing interactions? Okay, it will be overcome, right? So that's how solubility works. If they are attracted to each other enough, they will basically break up with their current molecules. Okay, it's like how cheating works. Okay, they are currently with their own partners, right? But then, of course, if they want to cheat with each other, and if they're attracted to each other that strongly, right, they will just break up with their current wives. That's the same idea. Okay. Anyways, guys, can you all remember the format of answering this kind of questions? Okay, when you form these new interactions, do you release energy or do you require energy? Okay, Noah, when you form bonds or you form interactions, you release energy. Okay, so I'm going to write down the format again one more time. I need you guys to just fill in the blanks. Okay, energy released from the whatever, okay, between the aldehyde and water is okay. So this is a very standard solubility explanation. It's all about the interactions that you form versus the interactions you need to break. Okay, we use energy here because energy is just an easier way to compare, right? Fill in all the blanks. I mean, with this diagram up here, I'm pretty sure you all know which interaction we're filling in. Okay? In exam, I highly suggest you guys to draw this out first. Identify all the interactions, then you can just blast everything out later. Okay? No, these are all the interactions that we have identified up here. You just need to put the correct ones in the correct boxes. Yeah. Okay. Right, Ken? Okay, let me just very quickly write this down. Aldehyde and water is hydrogen bonds. Now we know hydrogen bonds are rather strong, so it releases quite a big amount of energy. It's enough because the one over here is enough, right? Or sufficient. It's sufficient to compensate. Why sufficient? Because the question did say it is soluble, right? Soluble means it is enough to break the interactions that are already existing. So, what are the interactions in your aldehyde? Up here, right? PD-PD attractions and hydrogen bonds in water. Can see all this?
Yep. Hydrogen bond stronger.
Okay, now you have to understand, right? These hydrogen bonds, okay, we are not really like looking at it objectively, that this one is stronger than this one. Okay, we are looking at it in terms of, right, how much energy is being released in total. Okay, apparently this guy releases more energy from the from here than from the hydrogen bonds in water. So you should never treat it as if the hydrogen bonds are like equal in strength. Okay, it's usually always different. That's why they don't really ask you guys to predict solubility. Okay, you infer from the question. The question says soluble, which implies that these red color interactions release quite a lot more energy than these black color interactions. That's how you infer over here. So you don't actually need to. Okay, good. Now with that said, okay, I just need you guys to go over to page 9. Now, this is where your organic stuff begins, and I've already told you guys how to study this in your cheat sheet as well. Okay, so let me just reiterate what I require of you guys. Again, right, when you study your reactions in organic chem, I always told you guys to split it into reactions and then synthesis. Remember? Okay, so reactions, then synthesis, right? I'm going to go over synthesis first because it's easier. So that's why you look at page 9. As I mentioned before, we have already learned all these synthesis reactions in previous chapters. It's all listed over there. I don't want you guys to refer to the notes because you see page 9, right? You're not space, right? What I want you guys to do is to write everything around on the board on page 9 again. That's what you need to do right yourself when you revise the chapter. Okay, so anyways, okay, let's start with synthesis first. Okay, now we already started learning carbonyl compounds right in the previous topic. So this one, your memory should be quite fresh off your head, right? Okay, so for the first reaction, I remember I required 3 things. Okay, I need you all to tell me what's the type of reaction, and then the reagents and conditions, and finally come out with a balanced equation. So guys, can you all tell me, right? Okay, the first one you all can see is from primary alcohols to aldehydes. What's this reaction called? So you must try to recall yourself and just tell me this is oxidation. Okay, oxidation of primary alcohols. Okay, we'll talk about a few things here because all these are very menial. Okay, everything's already in the notes. Can someone tell me what's the reagents and conditions? Okay, dichromate, yes. What else? Okay, must use H2SO4 finally. Heat, is it just heat? Okay, I want you to recall something. When you oxidize a primary alcohol into an aldehyde, is that the only thing you can oxidize into? It will further oxidize into carboxylic acid if you're not careful. Okay, why can it further oxidize? You all remember the criteria for oxidation? The carbon over here must have at least 1 hydrogen. Can you remember that? The carbon atom must have at least 1 H, so it oxidizes here. You look at the same carbon, does it at least have 1 H still? Yes, right? Okay, so you oxidize even further. Can you see that? Okay, today our focus is to obtain an aldehyde. So, can you just let the oxidation run well? No, right? You must, as I mentioned before, control the oxidation. Okay, so in this case, perhaps you can add in. This is control oxidation. So in order to control the oxidation, what are some ways you can do so? Okay, we use K2Cr2O7, H2SO4, last one is what? Okay, we have a heat with immediate distillation. Because if you don't distill it immediately, what will happen? You leave it there long enough, it will turn into carboxylic acids. And that's not what we want. Okay, other than that, guys, can we use KMnO4? Why cannot use KMnO4? It is too strong, no matter what you do, it's just gonna jump straight to the end. Does that make sense? Okay, later I'll come back to this reaction because we're gonna go backwards later. Okay? But for now, I need you all to take note, this is controlled oxidation. not the full-fledged oxidation over here. Okay? Any issues here? Now, just to show you guys what is coming later, right? If you can control the oxidation, however, later if there's oxidation, there will be, what's the backward reaction called? Reduction, right? Later we'll focus on reduction. I'll tell you quite a few details there. But right, if you want to reduce, right, to an aldehyde, you can reduce a carboxylic acid, right? Is that true? Can we reduce a carboxylic acid to an aldehyde? Actually, that's not possible. So I'll tell you first, the blue color arrow represents reduction. If you reduce a carboxylic acid, you go straight into a primary alcohol. Later we'll come back to this. There is no way you can reduce a carboxylic acid back to an aldehyde. So I suggest you draw these arrows and then the cross on the arrow over there. So like that, right? When you all put your cheat sheet, at least you know what these arrows represent. So I say again, you can control the oxidation, but you cannot control the reduction. I'll repeat why later. Okay, first. I'll just go over the second reaction very quickly. Okay, the second reaction is the oxidation of secondary alcohols. Guys, when you oxidize secondary alcohols, what do you get? Okay, there's only one other functional group, right? Primary oxidized with aldehyde, secondary oxidized with ketone. Reagents and conditions. Now, do I need to be controlled in this approach? Okay, why cannot? Why no need? Okay, same thing, you all check this carbon. Does it have a H? Yes, that's how you get oxidized. But that same carbon, does it have a H now? It doesn't have a H, it's going to stop here. So is there a need to control the oxidation? No, right? If you don't need to control the oxidation, can I use KMnO4? Yes. Either dichromate or KMnO4, it really doesn't matter over here. Do I need to keep with immediate distillation? Why put in the extra effort? There's no point, right? Okay, just heat under reflux or just put that heat. That works. Okay, it's not very simple, nothing for me to discuss. What I want to discuss is the last way of synthesizing aldehydes and ketones. Okay? Okay, so far any questions? Okay, the last reaction is oxidative cleavage. It's been a while since we talked about that. Guys, can you tell me, right? What functional group here undergoes oxidative cleavage? Okay, alkenes, good. Okay, so an alkene oxidizes and will cut the double bond, right? Okay, oxidative cleavage, right? I need you all to have examples one. So when you do your cheat sheet, right? I really need to see you guys putting in examples that I'm going to give you today. Okay, but anyways, this is the part. This is a very important reaction, so I'm going to go over in more detail. Some of the simple things out of the way first. Guys, what's the reagents and conditions? Oxidative cleavage is also known as strong oxidation, right? Now you see the word strong oxidation. Can you use dichromate? No, you use dichromate, nothing will happen. We also use KMnO4. And then the rest is the same, KMnO4, H2SO4, and T. Okay? Simple stuff. But guys, what I want you to take note from now on, right, which will help you guys in elucidation questions, is to know what are the products of oxidative cleavage. Now, there are only 3 products in oxidative cleavage, and I need you all to take note. Can you tell me what are the 3 products? Okay, good. Carbon dioxide and water, or just carbon dioxide, right? Okay, whatever, on the right move. What else? Okay, good. Ketones, that's the third one, and then the second one is carboxylic acids. Yes. Okay, guys, you all have to understand what is this topic for today. Today we are learning aldehydes and ketones, right? Hey, how come I can't get aldehydes from oxidative cleavage? Why? What's going on here? What happened to the aldehyde? Okay, yes, do you all realize aldehyde will oxidize further into carboxylic acid? So there's no way you can obtain aldehydes. And I know it's very obvious to some of you guys. But I'm going to write down first, cannot get aldehydes from oxidative cleavage. Because guys, even if you form an aldehyde, what will happen? What did we discuss earlier? What will happen to the aldehyde? It will oxidize even further to carboxylic acid. What causes it to oxidize further? Look carefully at your reagents. What do you use over here? You are using KMnO4, right? So KMnO4 is already mentioned that you cannot use over here because it's so strong that it will oxidize the aldehyde straight into carboxylic acid. So that's why it's impossible to get aldehyde for oxidative cleavage. On one hand, you need KMnO4 to break the double bond. You need something very strong to break the double bond. But on the other hand, the KMnO4 is so strong they will oxidize any aldehydes. So you'll never get aldehydes in this case. You must take note of this. Okay, you can only get ketones. Let me give you guys some examples. I'm going to start off easy first. Now perhaps right, draw the structures of this compound. Okay, I don't care about balance equation. I only care about your products. Okay, give me the structures of this compound first. We start off easy. Okay, start off easy. Okay, draw the products of oxidative cleavage for this very simple compound. Okay. Yeah, I'm just going to draw more also. When you practice oxidative cleavage, don't want you to just copy the simple examples in the notes. In the notes has the most rudimentary examples. And that one is very pointless. Okay, what I need to see are complicated molecules that you are practicing yourself. So you can come up with any weird looking alkene, right? And the purpose of all that is to make sure you know how to do your own oxidative cleavage. Okay? Yes. Okay, now when do you get carbon dioxide and water generally? No, this is oxidative cleavage. Generally, where is that alkene in order to get a carbon dioxide? Yes, good. Okay, so carbon dioxide and water, one of which is to see a terminal alkene, spot for a terminal alkene. But there's actually another way, and we're going to talk about it in a bit. Okay, so guys, how do you get the first structure here? I think by now this is quite simple. Okay, I've taught you guys how to do oxidative cleavage before. You cut the double bond first, and the double bond must add a 1 now. Okay, you have two fragments, right? I'm just going to draw the two fragments. It looks something like this. Can you see that? This is after you take a scissors and cut this part. Now, when you see the double bond, you must add an O. So add an O to both. Can you see all this first? What else must happen? So if you can't remember, I'm going to write down the steps for oxidative cleavage. The first step, you must add O to any double bond that you cut. What's the second step? Yes, good. Add O to any H. Okay, you find any H's, you become OH. Are there any H's here on the first fragment? No, right? The second fragment have any H? Yes, that one have H over here, and that one must become OH. Now I'm going to draw the other structures. Okay, go. Okay, let me redraw this. Okay. Do we have 4 products all the time? Maybe, sometimes not necessary. Because I have 2 double bonds here, I have 2 double bonds here. You're going to count later how many products we have. You might not even get 4 products. You might get less, right? Or today the news come out say that in 2026 you can PW is pass fail, fucking easy. And then your what do you call that? Your form H2 subject, you can basically screw it. Yeah.
What are you doing all this? What do you mean by screw it?
Like
it's not
it doesn't count to your university admission score. Yeah. So let's say a weaker subject is like econs or some shit, right? Then just don't care already. But that's actually that easy. So yeah, that means you only focus on 3 subjects. The 4th subject just go in there and fail. No impact whatsoever. Oh, that's crazy. So easy. But unfortunately, your still cannot get that yet. 2026, wow, that's a bit late. Yo. What? No, finish it. Like 6 today. Oh, done yet. Okay, I'm going to look at the second structure now. Okay, let's look at this now. Okay, we have 2 cards, right? Guys, when you cut something 2 times, how many products will you tend to get? Normally get. No, it should be 3, right? Now, okay, you take a long line, right? Then you cut 2 times, then you should get 3 items, right? Does that make sense? Okay, don't look at all the what curve here, curve there. Just think of like logic, right? You should get 3 products most of the time. Okay, so guys, you cut once here, cut twice here. Okay, so you see, what are some products? Can you tell me the most obvious one? Okay, because we have a terminal alkene, right? So you can just tell me your carbon dioxide water, yes. Okay, I'm not considering water as a 4th product, by the way. Yeah, I'm saying like, okay, if we consider organic products only, then I'm going to say carbon dioxide. I don't care about water. Okay, if we're looking at organic products only. Next, guys, look at this segment over here. What should I get? So you can draw. Here must have a carboxylic acid. You can see that. Afterwards, over here must have a ketone. All I'm doing is just following my 2 steps that I have written out up here. Does that make sense? Okay, don't forget, yeah, okay, so some of you guys are getting aldehydes. If you forget to turn this into OH, it's an aldehyde, yes. No. Okay, you must understand, right? You cut that time, you must look at it this way. This part over here is still together, they are not separated. Okay, guys, then you see the last fragments over here, right? Here, then I should get another carboxylic acid. Can you see that? So these are my 3 products. The last one you want to try out, this is very important. Okay, 2 minutes. Okay, go and try this. Where? Which one? Because we cut over here, there's an invisible H, right? So the H must become OH. Okay, last one is very important. You must have the last one in all your oxidative cleavage sheets, basically. Okay, or your alkenes, you must have this. Okay, you do it one more time, you must have this. Okay, no matter what, because this one has a very important example. Okay. Okay. Cut. Okay, you cut here, you cut here. The first thing that you should ask yourself is how many products do you have? Okay, you look carefully, Do you necessarily cut something 2 times and get 3 products? Okay, not all the time, because in this case, this is a cyclic structure, right? Look at it for yourself. You cut 2 times, but you get 1 product on the left, the other product on the right. So not all the time you cut, then you expect 3 products. Can you see that? Okay, we do this together. Okay, I'm going to do the right hand side first. Okay, so focus on the right half. The right half, right, I'm going to get a ketone here, down here. And then when I go up, I'm going to get myself a carboxylic acid. All you need to do, right, is just add the O's to the double bonds. Then add the O to the H. That's all we have. Can you see that? Okay, some must practice yourself. Okay, at the end of the day, it's all up to you guys. We get the left side of the compound now. Alright? So can you tell me this carbon over here becomes what? What functional group? There are only 3 possible answers here. What's this? No, okay. You have to get yourself a carboxylic acid. Okay, you notice when you cut, right, it's this fragment here. Can you see that? The O must the double bond must add a O. Can you see that? Add the O here, add the O here. Anything else to add? Okay, all the H must become OH. Okay, oxidative cleavage, right, is a test of your visualization. If you can't see all this, that means your visualization need to practice. That's why, right, you must come up with all these answers yourself, all these structures. Yes. Okay, yes. Guys, if you draw this last thing and you leave it as this, it's wrong. Because what is this actually? Okay, so let me draw a bigger version of it over here. This right here is a double carboxylic acid. You can see that? Both carbons are a carboxylic acid each. We call this ethane because 2 carbons. And then dioic acid. Oic acid means carboxylic acid. Dioic just means 2 of the carboxylic acids. Guys, this is a very important structure. Because can I ask you all, does this guy stay as like that? What does it actually become? This guy will further oxidize into 2 carbon dioxide and water. Take note, it will further oxidize, which means to say it is not possible for you guys to draw this as your answer. You must realize it already. And right there, 2 carbon dioxide. You can put the water there also you can. Okay? So guys, when it comes to carbon dioxide and water, there are 2 ways to produce it. One is terminal alkene. Okay guys, one is the terminal alkene, right? The other one I need you to take note is ethane dioic acid. I know the name sounds a bit funky, but I really need you guys to remember the name. When do you have ethane dioic acid? Let me give you a bit more clues here. You take a look at this compound. Normally, when you see a double bond followed by a single bond, followed by a double bond. So notice this pattern. Double, single, double usually will ethane dioic acid. So I'm helping you guys recognize patterns. Okay, but you must verify. Don't just see any double, single, double, then just tell me it's ethane dioic acid. You still must cut the compound yourself to go and verify. Okay, let me give you guys a bit more advanced information because now we're going to learn elucidation, right? We already learned last chapter. So today, you take a look at this. Terminal alkene is carbon dioxide, right? So it's a loss of how many carbons? Okay, I ask the same question. You'll take a look. When you have a terminal alkene, how many carbons do you lose? 1, right? Because terminal alkene is only 1 carbon dioxide, and you must treat the carbon dioxide as it fly away. Right? So, go and write this down. Terminal alkene will have the loss of 1 carbon. How about ethane dioic acid? Loss of how many carbons? 2 carbons. Why is this so important? Because, guys, in elucidation questions, oftentimes you need to look at the molecular formula to identify how many carbons are lost, and then you need to investigate why. So for example, they can give you a very huge compound that looks something like this. Again, it looks damn weird, right? But then, if suddenly they tell you that this guy becomes C9H, I don't know, C9H14 or some shit like that. Okay, then you know the loss of 2 carbons could be due to 2 terminal alkenes or just 1 ethane dioic acid. Can you see that? Okay, so let me give you guys don't write this down. Look at the serial example. Okay, if let's say I have this compound over here, how many terminal alkenes do I have? I have 2 terminal alkenes, right? Now is this the double, single, double pattern? It's not, okay, look carefully. So in this case, can you draw this compound out? Tell me, there are 2 terminal alkenes. That's why this one will lose 2 carbon dioxide. Okay. On the other hand, guys, can you look at this compound here? How many terminal alkenes are there in this guy? How many terminal alkenes? None, right? There's no terminal alkenes, but what do we have? We have the double single double pattern, which means we have ethane dioic acid. All I'm trying to say is this: in elucidation, sometimes right, you will see the loss of 2 carbons, but it's not very conclusive until you have enough evidence. It could be 2 terminal alkenes or ethane dioic acid. I need you to take this down. Okay, I know I spent quite a good amount of time on this. Okay, it's not related to carbonyls, I know. Okay, but I feel that this is important enough that you will see it very soon. Okay? Telling you as much information as possible. Okay, when take note of all of this, I'm going to erase the rest, the not very important stuff. Any questions so far? Okay, very important. Huh? Okay, then from there, right, pretty sure you all can flip over a couple of pages. Hey guys, move over to page 14. Okay, 13 or 14 now. Okay, same thing. We're gonna now start on reactions. Whatever that we've gone through so far are called synthesis. Now, reactions means what? Means the aldehyde or ketone can undergo further stuff, right? Okay, so take a look. The main reaction, we're gonna list down the reactions first. Okay, the first reaction we're gonna understand, right, is nucleophilic addition. Okay, I don't want you to just memorize the name, right, and attribute it to whatever functional group. I need you to understand why it's called nucleophilic addition. I think to start things off, right, can you all tell me why is it called addition? Not really. Okay, that's not the reason for it. Addition versus substitution, right? Okay, I need you to take note, right? What kind of compounds undergo addition and what kind of compounds undergo substitution? I hope you remember the term of unsaturated compounds. Yes, unsaturated compounds contain somewhat of a double bond. Or yeah, okay, let's just keep it at that way first. Okay, there's a double bond in unsaturated compounds. As you can see, right, in aldehydes and ketones, we have a CO double bond, so it undergoes addition. Unsaturated means what? Can you remember? Okay, you have less than 4 atoms around the carbon. Remember, carbon can hold a maximum of 4 atoms. And for that to happen, you must have all single bonds. You can see that. This is known as saturated because you have a maximum of 4. However, if you have a double bond, how many atoms are there around carbon? There's only 3, right? No. Oh, is it 3? Well, yeah, maybe I haven't shown properly, my bad. Okay, but anyways, yeah, unsaturated means there are 3 atoms, right? That means you can add more stuff. Okay, but I don't want to, it's not that important. Okay, what's more important is, guys, why is it nucleophilic and not electrophilic? Okay, I always tell you guys to look at the functional group, right? Okay, look at the functional group here. Can you tell me a carbonyl compound? Is it electron rich or electron poor? Okay, wait, what? No. Why would they add the rich? Okay, guys. That's not the correct reason. Carbonyls are electron poor, but can you tell me what exactly about carbonyl compound makes it poor? I'm going to draw a quick carbonyl compound here. I need you to tell me, right, which part about this molecule makes it poor? No, it's not. Can you tell me which atom in particular is electron poor? Which atom come? Which part about this molecule is poor? This carbon in the middle, right? Why? Because it's bonded to the very electronegative oxygen one. So the idea is that it's electron poor because of the carbon, right, in the C double bond group. Now, if it's electron poor, that means it must be attacked by what? Something that's electron rich, which are essentially nucleophiles. That's why, guys, this is called nucleophilic addition. Yes. Oh, okay, that will come to it later. Okay, but right now I'm just saying in general, right? Yes, you might have methyl groups donating electrons, but it is the carbon here still makes it poor because oxygen is very electronegative. Oh, yeah, okay. Fundamentally, it's poor. Later, I'll tell you all how this is related. You're right, okay, but that's not related over here yet. Okay. Now, guys, okay, take a look at next. Now that we know the name, right? I'm not going to go into the mechanism yet. Later, then we look at the mechanism. Okay, but for now, there are just some things that I need to mention. Okay, you just need to know right now what are the details of nucleophilic F. Okay, I'm gonna come out with the reagents and conditions like before. It's a very specific one. I need to memorize this. KCN, trace KCN, and co. Guys, what does trace mean? Very little, yes. Okay, you only need a little bit and we will understand why later. Okay, or maybe you guys can guess right now. If you add only a bit of KCN, right? What does that imply about KCN? It acts as a what? Usually the thing that you add very little of, right, is the what? The catalyst, yes. Okay, so guys, because it's trace amount, right? This guy is actually acting as a catalyst. Now the reason why it's cold is very stupid, because if you put too hot, right, then HCN will turn into a gas and then you inhale, you will die. Okay, so it's cold so that HCN is a liquid. You see that? Okay, so you won't die. Okay, but anyways, that's not the important part. The important part here is the equation. Because I need you all to recognize how this looks like. I'm gonna have the smallest aldehyde possible, just to make you guys see how it works first. Okay, when you add HCN with a trace of KCN, look at what's gonna happen. Listen to me carefully. The double bond O is gonna become OH. And because it's addition, I'm just gonna now add a CN. Can see that? That's all I'm doing. Okay, that's all I'm doing. Okay. Okay, let's look at more examples. So perhaps write down another equation. Okay, I'll go and write down the product. Draw the product of the nucleophilic addition of this guy now. Now try yourself, but if not, okay, you wouldn't know how to do it yourself. Okay. Okay, and furthermore, the notes always give structural formula. I'm not a fan of structural formula. You all must draw skeletal. Okay. Okay, how do we do this? Okay, so same thing, guys. All the carbons I do not need you all to touch. The double bond O becomes what? OH, and then what do you do now? Now just add a CN on the same carbon. So guys, what this is called, when you have OH and CN on the same carbon, this is also known as a cyanohydride. Now you do not need to know this guy's name. No need. But all you need to know are the individual functional groups in this guy. Can you tell me OH is what? Okay, OH is alcohol, right? And CN is nitrile. When these two guys combine together, it's called cyanohydride. Now let me just quickly talk about one more thing, because I need to take another shit. It's quite bad. Wow. It's quite bad. Okay, so guys, now let's take a look. Before I give you all some questions to do, okay, I need you all to understand something. You look at this reaction and tell me, guys, what happened to the number of carbons? Increased by 1, right? Because I mentioned before, anything involving nitriles will step up the reaction. So, step up reaction now, we have learned 2 types. Okay, the second type is we learned today, nucleophilic addition of carbonyls. First one was what? Do you remember? Okay, can you remember the first one? The halogen, right? Okay, so the nucleoside of halogen alkanes. Okay, and I can't talk about it more already. Okay, let me just give some examples for you all to try out. I need you all to get from this guy all the way to this guy. Okay, try these compounds while I take a fat shit. Wow, actually quite bad. The mala is kicking in. Okay, so anyways, I need you all to try, right, these 2 questions. Come up with a synthesis pathway, draw all the steps. Okay, so I'm going to discuss if you need to. Okay, wow. Okay, have you all managed to get the structures?
So you know that thing on there.
Huh? Just give up.
Okay, wait.
The first one at least can do, second one cannot, never mind. Okay, let me give you guys a bit more info. Okay, maybe you can try this again. Okay, there are 2 types of step-up reactions, right? Okay, and I'm going to draw a small little equation, right, to show what's happening. Okay, so this was the nucleophilic substitution with the nitrile. The number of carbons will increase. Now for the second version, right? Today we learned that carbonyls, when you undergo nucleophilic addition, you will also get yourself something like this. Now there's a way, right, to make things even easier for you guys. Okay, there is a way where you can actually determine which type of step-up reaction it is. So let me tell you this now. From now on, right? If you see the number of carbons increase, that's number one. But the next thing to check out is there a change in number of functional group? Okay, as you can see over here, is there a change in number of functional group in the first version? No. Okay, you still have only one functional group. How about the second one? How many functional groups are there in the second one? Two, right? From one functional group to two functional group, there is an increase. Hey guys, if you have an increase in number of functional groups, that means you should choose the second version to step up your compound. If the number of functional groups never change, then you should use the first version to step up the number of carbons. Does that make sense? Okay, so first version, second version. Two different types of nitrile reactions that can help to increase the number of functional groups. So can I ask you all, right? This first equation, this first question here, what happened to the number of carbons first? Okay, there's an increase in number of functional groups, yes. But then what's next? Yeah, you read the second one first, we try the first one. Yes, there's an increase in functional groups, but which one should we use? The first type of reaction or the second one? Yeah, how many functional groups are there here in the first starting compound? There's only one functional group here, right? Then here, then how many? Here we have one functional group also. Carboxylic acid and alkene one, only one functional group each. Can see that? So because the number of functional groups cannot change, you must employ the use of the first reaction to step up your compound, not the second version. Can you see that? Okay, so guys, we know that there has to be this reaction in your synthesis pathway. So now, instead of just getting from the start to the end, let's change it up. We know that the start must first get to a halogenal alkene. Is there a possible way to turn an alkene into a halogenal alkene immediately? Yes, right? Where do you put the halogen? On which carbon? Look at the final compound. Where do you think you want to put the halogen? On the second carbon, right? Because that's where all the reaction happens. So guys, look at this first. I have now successfully changed my alkene into my halogenal alkene. Then now, what do you think the next step is? Yeah, exactly right, guys. I already mentioned that this guy is going to end up stepping up the reaction. So we know that this reaction is bound to happen. Then we already know what the next reaction is like. We change this into a CN. And now our final job, right, is now that we have stepped up the compound, then we can turn this into the final structure. Can you all see, right? How we just approach this question is not just to think how to get from the start to the end. I actually split it up into three parts. Part one, I go from alkene to halogenal alkene. Part two, a halogenal alkene to nitrile. Part three, nitrile to the final compound. Guys, how do I turn a nitrile into this functional group? So this time you all need to know the nitrile reactions. Nitrile can turn into carboxylic acid. You remember what this reaction is called? This is acidic hydrolysis. Can you see what's happening? Step-up reactions will save your life because it will help you segregate the synthesis pathway into multiple smaller and more manageable parts. So guys, this is your pathway, and now they are marking for your reagents and conditions. Can you tell me what's the first step reagent and condition? What are you doing here? What am I adding? I'm just adding HCl gas, right? And the actual failure addition room temperature is okay, so you don't need to write anything, but if you ever write room temperature is fine also. Can? How about the second step? From Cl to Cn, what do we do? Okay, good. It's not just HCN, the solvent must be ethanolic KCN. Okay, so ethanolic KCN and what's the condition? Heat. Heat because you need to break the very strong single bond here, the very strong sigma bond. Here you're only breaking the pi bond, that's why it's room temperature. Okay, I repeat here pi bond is only broken, so that's why room temperature is enough because pi bond is very weak. But here you have to break the entire sigma bond, right? Sigma bond is a lot stronger, so you need to heat it. Does that make sense? Okay, then finally, guys, how do I turn CN to CO2H? I mentioned acidic hydrolysis. Acidic means H2SO4 aqueous, and hydrolysis usually need to heat. Okay, so that's the idea. Hydrolysis means breaking bonds using water. I say again now. Hydrolysis means breaking bonds using water. So if you want to break bonds, right, generally the bonds are quite strong, that's why you need to heat it. Does that make sense? Now guys, I want you to employ whatever I just told you, right? And then try the second question. The second question, this is what I ask you guys to do. Turn this compound all the way into this compound over here. Later at the end of the lesson, right, we're going to try another question that is very similar, another synthesis pathway. Okay, but for that to happen, you all need to know how to do all these simpler pathways first, because that one later, right, not so simple really. Okay, come, go and try this. With the rules that I've told you guys right now, okay, this one should be a lot easier. Okay, so a few minutes. Okay, basically this entire topic, right, the main thing is nucleophilic addition, right? So that's why I'm spending more time on this. Okay. Well, I think just now some of you guys came in late, right? Okay, do know that March holidays. Okay, I need you guys to come down. Apart from the normal lesson, you need to come down another time. It's for free. Okay, but it's to do mock paper. So I give you all mock paper and then you all just sit down here. Yeah, okay, no choice. Need to do mock paper before the exam. Okay, there's sometime in the March holidays. When the date will be, I'll tell you guys again. Okay. Okay, remember all the principles first. You approach the synthesis question. What's the first thing that you must always do? Check the number of what? Number of carbon atoms first, actually. And what do you realize is in this question? I think I draw the compound wrongly on my bad. No. This is not the correct compound. Okay, I am referring to this. Yeah, my bad. Oh, okay. Try again, my bad. That was a problem on my part. In synthesis pathways, they usually got a lot of hacks to it. That's why if you know your reactions well, right, this kind of questions can score. If you want to know the first question, how many marks, right? It's 5 marks.
Huh?
Yes. Why 5? Because 1 structure, 2 structure, and 3 reagents and conditions, 1 mark each. 5 items. And it's very easy to score if you know your reactions well and if you know all the hacks that I tell you. Okay? So come, let's try this second reaction, guys. What do you notice about the number of carbons? Okay, increase in 1 carbon, right? So that means it's a step-up reaction. Now, what's the next consideration? So you first count the number of carbons, and then the next thing is to count the number of functional groups. Because we know that step-up reactions, you can actually check the number of functional groups. What happened to the number of functional groups? Increase, right? So guys, which step-up reaction should I use? The first or second? The second. Can you all see that's your thought process? So we already limit our answer, right, to this. This particular reaction must happen somewhere in my synthesis pathway. I don't know where, but it will happen. Now, instead of getting from the start to the end, I'm making things easier. I'm getting from the start to where? Start to the carbonyl group first. Can I turn this guy into a carbonyl? Is that possible? Yes. So what shall I do here? This is a what kind of functional group? This is a secondary alcohol, right? And it will be turned into a ketone. Good. Okay, so first reaction here is an oxidation. You turn the OH into a double bond O, and that's pretty much it. Guys, what's the next step? So very simple. What's the next step? You already know. Yeah, it's the step up reaction, the nucleophilic addition, right? So you know that this is bound to happen. I already got mine covered now. So I know that the second step must turn it into a that thing there, cyanohydrate. From here, right? Okay, go and complete the thing. Okay, I want you to know how to draw the structure of the product of this nucleophilic addition. That's the part that is new, so I need you all to practice. Okay? Yeah. So guys, next time you all see step up reaction, you should be glad because it's way easier. Imagine the number of carbons never change. It's not step up, it's not step down. Then how? That one's harder. You have a lot more options to consider. Okay, so guys, okay, the next structure that you can draw, again guys, the alkyl groups, all the carbons are the same. The double bond turn into what? The double bond turn into OH, and then what? You must add the CN on the same carbon now because this is two functional groups on the same carbon. Okay, now guys, is there a way to turn this into the final compound? What do we do? As you mentioned, you see CN turn into CO2H, it's the same shit as before, right? So in this case, it's still H2SO4 and heat. Guys, if you know your reactions, some of these reactions and conditions are really free marks on. Okay, let me write down the reaction in blue marker. Okay, this right here is acidic hydrolysis of nitrile. The second step is nucleophilic addition of carbonyls. Okay, which is what we have just learned, KCN, trace KCN, and coal. Right? Yes. Okay, this is in halogenal alkenes. Halogenal alkenes for a small segment of nitriles. That's why I tell you, I cannot ignore nitriles. Okay, and finally, guys, okay, you need to oxidize this first reaction. Okay, secondary alcohol doesn't matter. I'm just going to use any oxidizing agent. Finish. Okay, so take note. These are questions that can come up in exam. So guys, your cheat sheet, when you all do that time, right, I don't want you all to just copy from the notes. All these examples that I give in class, right, you must put it in your cheat sheet. You must do it yourself. Don't just copy and paste here. There's no point. You copy the starting and the ending product, then you do the question yourself again. Okay, that's the only way to use. Okay, can? With that said, there are some very medial reactions here and there. Let's just cover some of them. And then I'm going to touch on the nucleophilic addition a bit. Okay? Okay, honestly, this chapter, not that much content. Okay, I think it's very, very doable actually. Okay, compared to the previous topic, I think this is slightly better. Okay, and then after carbonyls, right, you get way worse. Yeah, okay, way worse. The next chapter, no lah, as in carbonyls, the content is very little. You see these notes are actually very bad. Yeah. Carboxylic acid got two parts. Nitrogen compounds, I need 3 lessons. Yes, nitrogen compounds got acid-based titration. Okay, that one difficult. Okay, so really, I'm telling you guys to do the cheat sheet now, right? Is to help you all. Okay, when the next 2 topics come in, legit, those 2 are quite hard. Okay, that's why no choice. Carbonyl considered easy already. Okay, anyways, guys, let's move on to the next reaction. Next one is reduction. Now, the only thing I'm going to discuss for reduction, right? Now I'm going to give you guys a complete picture of all the reducing agents in your syllabus. Meaning to say you'll never need to worry about this again. Okay? Okay, first of all, very simple stuff. Your aldehyde can reduce into what? Okay, aldehyde reduce into primary alcohol. Okay, and ketone can reduce into a secondary alcohol. Okay, simple stuff. Now for these two reactions, can use all the possible reducing agents. Okay, so let me show you all. I need you all to write down some things. Okay. Now, reagents and conditions is a reducing agent causes reduction. Yes. Okay, but guys, I'm going to introduce all the possible reducing agents because in this particular reaction, you can use all of them. LiAlH4 is dry ether, or you can use H2 nickel catalyst at high temp and pressure.
All of this is
Okay, this is in the notes also. Okay, but I want you to add in stuff. Okay, there's a third reducing agent called sodium borohydride in methanol. Both for the first and the last one, I add room temperature. Now, guys, what I need you all to now write down, right, is this. There are so many reducing agents, so what can they reduce and what can they not reduce? Okay, over here, I'm going from the strongest reducing agent to the weakest reducing agent. So let's start with the strongest. The strongest means what, guys? Do you think it can reduce a lot of things or very little things? A lot of functional groups can be reduced, right? In fact, guys, I need you to take a look. For LiAlH4 and dry ether, it can reduce everything except alkenes. So generally speaking, guys, if you can't remember your reducing agent, you can at least whack your lithium aluminium hydride, and there's a high chance you'll get your answer correct. If you put it for alkenes, then I'm sorry to say you're wrong. Okay, so I tell you all right now. Okay, now let's go to the weakest. Sodium borohydride is so weak that it can reduce a lot or reduce very little. Very little functional groups. And because of that, it can only reduce aldehydes and ketones. Basically your carbonyls. Now then we have the mid tier. The mid tier can reduce more than the last guy, but less than the first guy. Make sense? Okay, because you are the mid tier one, right? So because of that, you can reduce aldehydes and ketones also. Correct? I mean, if the speakers one can reduce aldehydes and ketones, you can only expect this guy to also do the same thing, agree? Okay, it can also reduce a few more extra stuff like nitriles, and finally alkenes, because alkenes cannot be reduced by anything else except for H2 gas. So alkenes here is kind of important. Okay, but you all must take note. This guy can only reduce 2 things, this guy can reduce 4 things, this one can reduce everything except for alkenes. Quite easy to remember. I tell you right now, because I used to tell everyone at the end of the syllabus, which I find that's a bit pointless also. Okay, so now that you all know, you just gotta remember all 3 reducing agents. Okay, can? Now, as mentioned earlier, right, let me just very quickly touch on this again. Primary alcohol oxidized into aldehyde first, correct? And then afterwards is carboxylate acid. Now, the first reaction here is it must be what? It must be controlled, right? Now, the first reaction is controlled, second reaction is just further oxidation. Guys, but I mentioned just now, right? For reduction, can you all tell me, to reduce a carboxylic acid, which one of these reducing agents must I use? LiAlH4, based on whatever I told you, right? Okay, carboxylic acid can only use LiAlH4. Can see that? And because it is the strongest functional group, it will reduce all the way back to primary alcohols. Can see that? But then what's next? Okay, can you all now tell me, right, why it can't reduce the aldehyde? Based on whatever I told you over here, why can't the carboxylic acid just reduce the aldehyde? Okay, good. It's so strong. It's so strong that even if you get aldehyde, what will then happen? Aldehyde will then reduce back to primary alcohol. Can you see that? Okay, then some of you guys might ask me this. Okay, lor, then use something weaker lah, so that it can reduce just one step. Right? But guys, as I already mentioned now, can carboxylic acid even be reduced by any of these guys? No. So not possible. Can see that? Okay. So good that you're thinking about this. It's not possible for this to happen. If you use a weaker reducing agent, just nothing will happen. Okay, unfortunately. Okay, but of course there are other ways beyond our syllabus to synthesize this to have this reducing power. Okay, but of course not on the syllabus. And so far. Okay, go and write down this. So when you all revise, right, I don't want you all to just write oxidation. I need you all to write down the backward arrows for reduction also. That is a complete picture. Okay, can? So you start to link everything together yourself. So not so segregated already. Okay, I'm gonna give you guys a bit more information on how these guys, these 2 foods, act as reducing agents in the first place. Okay? Okay, I'll just come to it in a bit. Okay, and later after we learn the mechanism, I might show you guys another example. Right? Let me erase this. Guys, one thing that you will probably be tested on, like last time they never test one, but then now they start testing more. So I'm going to tell you guys as if it's part of the syllabus. Okay? Can I look at Al1, AlH4, and NaBH4? How on earth, right, do these guys even act as reducing agents? Okay, so let's take note of some facts first, and then we come to the details. Both of these guys produce this thing called a H minus. Now, is this a nucleophile or electrophile? H minus.
Electrophile.
No, it's not. Okay, nucleophile because nucleophile is big. Yes. Okay, guys, take note.
Oh my goodness.
Come on. No, at least you're still trying. That's good. That's what I want. Okay, so guys, I mean, if you don't say anything, I can't correct you also, right? Okay, so you must know. Okay, you must say. You don't be afraid to say. Okay, so you produce H minus nucleophile, yes. So it's actually the H minus nucleophile that does all the work in doing the reducing. Does that make sense? Okay, so let me just show you guys. Okay, I haven't teach you all the mechanism, so later I'll come back to the mechanism. Okay, but for now, I need you all to perhaps know a few more things. Yes, they produce H minus nucleophile. So can I ask you all, right? We know who's stronger. Who's the stronger guy? LiAlH4, right? Okay, so we work backwards a little bit. Okay, if LiAlH4 is stronger than NaBH4, so now we're talking about strength. What does that imply about him producing the nucleophile? It's more, right? He is more able to produce the H minus nucleophile. Can you see that? Okay, that is inference. Okay, so LiAlH4 is stronger, implying that LiAlH4, okay, it produces so-called more of the H minus nucleophile. Okay, so if we don't say more, maybe we can say produces H minus ion more easily, okay, than NaBH4. But why? That's the question. Okay, why does it produce NaBH? Why does it produce a H minus ion more easily? Okay, so guys, why I'm teaching you all this way is because if you look at the next page question, is what they already said. They already tell you who is stronger. So you need to work off your answer from what they have told you. If they tell you it's stronger and you know it is this fact of the H minus nucleophile, that means you know, right? High chance it produces more H minus. But why? Okay, this one, your word, I don't expect you guys to know yet. So now let me go into the answer. Okay, the difference between LiAlH4 and NaBH4 is the ALH bond versus the BH bond. Okay, and here I can, now that I'll tell you the answer, but just now before that, you all need to infer yourself. Okay, that one is the important part. Okay, in this case, right, can you tell me who is less electronegative, Al or B? Okay, it's actually, B is on top, right? Al is at the bottom.
Oh.
So, Al is less electronegative. Okay, so Al is less electronegative than B, right? So that means what? The ALH bond is more polar or less polar? Okay, this one a bit confusing. So if you get it wrong, never mind. Let me just show you guys. It's actually more polar than BH bond. Okay, I'll show you guys again. Okay, but later, okay. Less electronegative, making the bond more polar. Now guys, if the bond is more polar, right, then you can all see. If it's more polar, that means the H minus nucleophile will be more easily formed. Can you see that? Since it's more polar, okay, LiAlH4 produces H minus ion more easily. And since it produces it more easily, we know that it is stronger. So what we could have done, what you guys could have done so far, right, is to infer this part over here. I tell you all that it is the H minus nucleophile that's responsible for the reducing. And then you all have inferred that the strength is higher, implying that you can produce more of the H minus ion. But why is it actually so? The root cause, right? I don't expect you guys to know this, I need to tell you all now, is because of electronegativity and polarities actually. Very common question, they will ask for maybe 1 or 2 marks. Okay, some of you guys will be confused with this part. How come less electronegative means more polar, right? Okay, use numbers, come. Okay, so look at this, electronegativity actually has a number assigned to it. The higher the number, the more electronegative. So guys, what are the most electronegative elements? Okay, it's like 4, right? Okay, F has a value of 4. In a unit, you don't even know, but it's to measure electronegativity. 4 is the highest number, right? Okay, let me just show you all what the values are for ALH and BH. Okay, one important fact that you all need to know, right, is that AL and B are actually less electronegative than H. That's how you're able to produce a H minus nucleophile. Can you see that? Okay, now next, BH, AL is less electronegative than B. Okay, I do not know what's the actual value, but you want to maybe tell me a value. Okay, wait, AL is less electronegative than B. Okay, you can tell me like 2.3, 2.4, right? Can you tell me which one is more polar now? Okay, now it makes sense, right? Okay, so you just put in numbers whenever you're confused. Don't go and guess, just put in numbers on the spot. Okay, now that's why now you all can see, since hydrogen is more electronegative, it is the one that actually forms the nucleophile. All okay so far? Can yeah, okay, this is a question that starts to get tested more and more often. Yes, the difference is greater, so the bond is more polar, higher electronegativity difference. Yeah, okay, use numbers. I last time also cannot imagine. Okay, I also need to use numbers. Any issues so far? Okay. Everyone needs a short break. Yes, no? 8 minutes. Okay, let's go up. Okay. Because then I took a fact sheet also. I mean, that was the break. Yeah. Okay, the thing is, by the next lesson, right? Okay, the next lesson, content-wise, I'm not going to cover much. Okay, most of next lesson is going to be the tutorial, which is more important. Okay, so I gave you a few tutorial questions technically already. Later we'll try one more. Okay, but now, guys, I want to talk about the nucleophilic addition mechanism. I don't think I can talk too much about it. Okay, I won't be able to go over every single property. That one we can continue next lesson because I want to focus a little bit more on the reaction synthesis questions. So I just want to go over one mechanism, how to draw, and then afterwards I give you all a question to do already. Okay, we won't cover that much more content. A bit no point, realize. Okay, guys, can you now turn over to page 19? Just now we mentioned nucleophilic addition, right? We are now going to draw the mechanism. Now, guys, what's the very first thing that you need to write down if they ask you to describe the mechanism? Okay, the name. Write down the name first. Title. Okay, let us consider the reagents and conditions. Remember, it's HCN, trace KCN, and co. And at the same time, let me just look at an equation that I have written out here. Okay, we look at the balance equation first, then later we draw the full mechanism. Okay, perhaps we can try to draw for this guy a ketone, okay, reacting with HCN with a trace of KCN to form the cyanohydride. So we got the reactants, we got the products. Now we can start on the mechanism. Okay? Okay, again, now guys, mechanism, this is not the mechanism yet. This is just details. Now let's draw. Okay? So once again, right, okay, go and draw, you go write down the title, nucleoadd. Okay, then we got your steps. Okay, we deal with step 1 first. Now I need you to understand, right? Just now I went through a little bit already. The carbonyl compound is it rich or poor? Okay, which part about the carbonyl compound is poor? Okay, the carbon that's bonded to what? Good, the carbon that's bonded to O is poor, right? So the carbon here is partial positive, oxygen is partial negative. If the carbon is poor, that means it must be attacked by a what? Rich nucleophile, agree? Now some of you guys will then draw HCN Because HCN is literally the reagent, right? But can you tell me, is there anything that's rich over here? Okay, no. Currently, even H, right? Okay, there's nothing rich about this compound. So what's gonna actually happen, right? Is we are actually gonna take out Cn minus here first. Okay. Now, can you all see that this is a nucleophile? Can you all tell me, right? How do we attack? Where is the lone pair of electrons? Is it on C or is it on N? Okay, some of you all will probably think N is a common mistake, but take note, it's actually on C. Why is it on C? It's because I need you all to take note, right? Hey, Cn minus comes from HCN, like that. How Cn minus is formed, right, is that these electrons are gonna come here. And that's why now it becomes H plus and then Cn minus. The Cn has the extra electron, that's why it has the lone pair. Can you see that? Okay, so we draw the full thing up. The N doesn't have the lone pair here that does the effect. C has extra electrons. So C actually has the negative charge and the lone pair of electrons. Okay, I know N still has a lone pair here, but that one is not like extra electrons. This lone pair is extra and it wants to give it away. Can you see that? Okay, so what you need to do over here is to take this and attack who? Attack the C. Now guys, okay, some of your mechanisms, right, I really see a lot of mistakes. Okay, I must see the lone pair being drawn. If nothing, right, it minus marks. Okay, and you must attack the carbon. If I see you all attack the partial positive, again, you minus marks. Then by now you have 0 marks. Right? Then what's the point of continuing, right? Okay, so please do this very carefully. But guys, is that the only thing that happens? Logically speaking, can you look at the carbon here? How many bonds does the carbon have now after the attack? Is that even possible? So what must happen? You must break one. Okay, who do you think you'll break over here? Okay, you all notice this is electronegative, right? I can break one of the double bonds. Okay? So one of the bonds here go to where? Okay, just go to O lah, because O is more electronegative. Start from the bond and point to oxygen. Don't point to any charges. So we have two arrows over here. Nucleophile attacking an electrophilic region. That's it. Rich attacking poor, right? Okay, now. Can you tell me, is this a slow step or a fast step? We're going to make a guess. It's a slow step. Why? Okay, first step doesn't mean slow step. Not all of them. Okay. Okay, guys, bonds are being broken. Okay, generally when you break bonds, right, probably a slow step. Man's on fire. Okay, so what's next? Guys, can you draw the intermediate? Can you see now the Cn is being attached? And guys, I need to see the bond to the C. I see a lot of people bond to the N, they minus another mark. Then by now you have negative marks. So I'm kidding. No such thing as negative marks. Okay, but then by now you basically wasted your time. Okay, guys, the O over there becomes what?
O minus.
O minus. Why minus? Hey guys, how come got minus? Okay, there's no H here, guys. Okay, the Cn is no H. Not yet, guys. One thing at a time, just follow whatever that I have to take. There's no H. Okay, it's okay. Later I'll show you guys where the H comes from. Okay, wait first. Okay, guys, why is there a minus? Because can you all see the oxygen is gaining electrons? Gaining electrons means you have a negative charge. Okay, that is your intermediate. You can see that so far. Can I ask you a few more questions? This carbon initially, what is the hybridization of this carbon?
sp2.
Okay, good. After that, then? Good. Okay, so guys, how do you know sp2 becomes sp3? Okay, good. Okay, good. Carbon now, the carbon is sp2. How do you know it's sp2? Because the carbon was a shape.
Just count.
Yeah, okay, trigonal planar. You can count the thing also can. Okay, and then carbon now becomes the intermediate, right? The intermediate now is sp3 because it is tetrahedral. Okay, you all need to think about this. You can test small little shit like that. Okay, you can think about the sign, right? Guys, clearly this isn't the final answer yet because I still have a second step. Draw in the intermediate first. Okay, guys, can you possibly tell me what's the final structure? What do you need to do? What's the additional thing you need to do here? Add the H. Okay, guys, you just need to add the H onto the thing over there, right? And then it becomes OH. So you draw the final compound first. Okay, you get something like this. Okay, so far. But guys, the issue is what's next? Where do you think you get a H from? You look at the reagents and conditions. This is all I added. Don't tell me water or anything. There's nothing. Okay, guys, can you tell me where do you think the H must come from? Where else? Okay, HCN, right? Okay, so guys, here is where the HCN comes in. Now, why I need you guys to really pay close attention to this is because a lot of people put HCN in the first step. And I don't blame you all, because HCN is the reagent mark. Okay, but it's actually CN minus first. In the next lesson, then I will cover a little bit more on why. Okay, it has something to do with kinetics and all that.
Wait, how come on top there's only the CN minus?
Okay, yeah, I just said next lesson, yeah, okay, because today we don't have time to cover the kinetics. Okay, maybe you want to know, right? If you want to know, let me just give you guys a bit more insight first, then next lesson I'll explain more. Okay, we already said that just now HCN, there's no nucleophilic enriched portion, right? That's why we can't use this as a rich thing to attack the core. That's one reason. That's why we use CN minus. Perhaps you can ask yourself, where does the CN minus come from?
Don't we have to show like
No, because where does this come from? That's why I'm asking this question. It comes from KCN. Okay, next lesson then I'll explain our guys. KCN, okay, since you all want to know, I tell you now. KCN is a weak acid. That's why it doesn't just give CN minus very easy. KCN is it will completely dissociate. It is a salt, right? It is a fully soluble salt, which will completely dissociate. And because of that, you will get CN minus automatically. You can see that.
you could just say that there, or you say
No, because again, KCN is a catalyst. You only need to add a bit, and that's why it's not involved in the overall reaction that now. Okay, to next lesson, I'll show you all the idea of why you need to add KCN. Why don't I add it? Why don't I, yeah, exactly, good question. Why don't I just add all KCN? Right, okay, never mind. Okay, that one next lesson we'll cover. Okay, for now, just know the mechanism first. Just draw this. Okay, but first of all, we're not even done.
how do you add on KCN where you get the H from?
Right? Like KCN.
Wait, what did you say? Add all what?
Huh? Sorry?
No, you said why don't you add everything?
Yeah, because some of you all will say, isn't KCN completely dissociating? Then isn't it better to just use KCN? What's the purpose of KCN?
Right? You need the H from
Yeah, that's why you need a H to make this guy the OH mark. That's why you still need KCN. Does that make sense? Yeah, okay, that's why they don't have shit for fun, right? It's all used for something. Okay, but anyways, guys, arrows, can tell me how the arrows move. O minus suddenly become OH. So what?
You must draw the
Okay, long back and first, good, then attack good. Attack the H because they must get together, right? Okay, how do you know you attack the H? Okay, good. But before that, one thing at a time first. O attack H, right? Implying that H is electron poor. Because rich must attack poor. So how do I tell the examiner that this guy is poor? Show a partial positive charge. Can see that first? If this guy is partial positive, that means carbon must have partial negative. Okay, then what is okay? Sanjay mentions the next thing. What else must happen? They must separate, right? The bond break already go to where? C or N. Now tell me. C, I already told you guys that it is C. I literally said over here, right? Okay, so it's the same thing over here.
Do we have to show the partial charges?
Must be in pairs, must be in pairs. Partial charges cannot exist alone.
No, like, so do we have to show like delta minus or O and then delta?
No. Pairs are saying like there's a plus, there must be a minus. Yeah, that's what I meant. Not the other side. Here cannot put partial charges, guys. O here is an actual negative charge. Okay, that one not related already. Okay, guys. Can I ask you one more question? Can you see? Okay, is to lead up to next week's lesson. CN minus. CN minus. What does this mean?
Is regenerated.
Yes, okay, guys. If CN minus is regenerated, then it is a what? Oh. Okay, guys, regenerated means what? It acts as a catalyst. That's why KCN, as I already mentioned just now, is small amounts because it's a catalyst. Okay? Alright, guys, another thing, one more important thing here. Carbon and hydrogen, is it a polar or non-polar bond? No,
No, what?
carbon hydrogen is non-polar, right?
There's not much difference.
But then now, guys, why do I have partial charges here? Can you all come up with a reason why? Nitrogen is very what? Very electronegative. So it will basically, possibly, right? Its influence is so strong that the electrons here will be polarized a bit. Does that make sense? Okay, that's why it actually makes sense here to have partial charges. Because the nitrogen actually is having a lot of influence. Okay, now I know we have like 3 minutes left, but I want to do one more question. Okay, or in fact, I need you all to try to draw the mechanism yourself. Okay, can you all look at the tutorial question 2? Okay, tutorial question 2, I need you guys to draw. Just do part A lah, huh? Right?
Level 1.
Yeah, level 1 question 2, part A.
Okay. I didn't highlight it here.
Yep. In the second part of the question, they're asking for other stuff, right? That one, then we explain next. Okay. Okay, let's try. Yeah, don't want to just copy straight from the notes. No point, just wasting your time. Okay, you must try yourself at least. Challenge yourself to see whether you can remember whatever. Okay, don't just give up. Don't just give in easily. Okay, to go and copy from the notes. Okay, later I need to see all your diagrams. Yeah. You count the number of carbons first. Then from there you draw the correct number of lines. Okay, correct. So 3, right? So the 3 lines there.
Then where is the
Okay, you see it's on the carbon on the right, right?
this one?
The last carbon.
Yeah.
Oh, the number of carbons you draw wrongly, but other than that, yeah, I'll just go with this. There are 3 carbons out, guys. Oh, missing some indicators here. Very first thing, missing some indicators. Partial color. Yes, correct. Maybe just going to fix the arrow. Okay, that's why I suggest you draw a pencil or something right there, you can change. Okay, let me just draw on the board also. Right? Okay, your carbonyl compound looks like that here. We have 3 carbons. Now the H is invisible because it's an aldehyde. Okay, ignore it. Okay, from now on, when again the question uses CHO, right? CHO is the aldehyde. Not COH, I also don't know why. That's just how it is. Okay, but anyways, you have this ready. You must first react with Cn minus. Now, it's not very simple. Cn minus, lone pair on C, attack this carbon. But how do I know I attack this carbon? I have to see your partial charges. Okay, partial charges on this carbon and oxygen. And then afterwards, the arrow must point from the double bond, one of the double bonds to the O. Okay, these are your arrows so far. Okay? From there, this is the slow step. The O must become a single bond O minus. And now you have a Cn attached to it. The first step is the most crucial because of all your arrows. Okay, let me just draw in red color. Okay, so far. Yeah. Then from here, right, then what do we need to do? Okay, the last step is very simple usually. Okay, because in this case, you are simply just taking the H from HCl. right? Lone pair on oxygen, B squared check. Lone pair on oxygen must attack the H. How do I know you can attack the H? Because the H is poor. Something like this. Break ready, make sure that arrow goes to C and not to N. Final answer. Looks something like this. Cn minus must be regenerated. Do not forget that. Okay, title the mechanism must be there as well. Okay, do not forget the title. Any issues over here? Okay, nucleophilic addition. Our next lesson, I'm going to recap the mechanism, and we'll talk about kinetics and the reactivity of aldehydes and ketones. Those are very important as well. Okay, so 3 different things in this entire segment. So next lesson, I'm going to reiterate this one more time. Okay. Okay. Yeah. Okay. Wait, I got CN. Yeah. Okay. Okay. Anything you want to clarify with me so far? Okay, don't have, right? That's it for today. Okay, today again the focus was more about the reaction synthesis pathways, the step-up reaction. Okay, mechanism I show you guys a bit over here. Next lesson, that's more of our focus. Okay, we got a few more distinguishing tests and all that. Okay, and then afterwards we'll do mostly tutorial. Please bring the tutorial next week. Okay, do not forget to bring tutorial. Okay, then afterwards again tutorial. I'll ask you guys to do some homework from the tutorial. Okay, and just to clarify, right, homework, right, I don't check already. Okay, you guys check your own answer. If you don't understand the answer key, then you ask me. Okay, because I have no time to mark the homework because now my priority, right, is all the cheat sheets that you guys are doing. Okay, can?
I think when are we going to submit?
Okay, anytime you're ready with like 1 or 2 chapters, right? Okay, don't rush it. That's why I don't give deadline. Yeah, okay, but you must do for the first couple of chapters first, like maybe the first and second, then you submit to me first, because there's bound to be a lot of errors inside. Okay, then I fix already, right? Give you like feedback, then you fix that, then afterwards you can proceed to the other chapters yourself. Then I'll tell you what is the instructions. I'll just follow you the message. It's basically organic preparation, okay, to prepare all the content and all the stuff that require. It's not just content, there's a lot more stuff also. Yeah. Okay, and with that said, that's it for today. Okay, see you guys.